Thanks. Hello, everyone. It's my great pleasure to be here. So I will talk about some aspects of beyond worst-case mixing time analysis in quantum Gibbs sampling. And I should give you a heads up that this talk is more on the physics side, and it's a relatively early stage. But I hope you will find this interesting. And also, we will also have some discussion at the end where I will sort of address and extend some of Anker's remarks. OK, so let me start by mentioning a perspective which I think could be useful for this workshop. The perspective is the following. So I think that intuition from condensed matter physics and quantum error correction can actually provide deep new insights into quantum Gibbs sampling. So for us, this is an excellent opportunity to bridge different fields. So in that spirit, let me ask a fundamental question about nature. The question is, does nature have the ability to create logical order by itself in a finite temperature environment? So if you don't know what topological order is, that's completely fine. So we'll immediately see how this connects with what we have been discussing in this workshop. So in our quantum Gibbs sampling field, the very first picture you think of is this arrow. So I should clarify that this arrow is in the opposite direction from Anker's arrow, because here I use temperature instead of beta. So in many classical and quantum systems, we have this behavior called phase transition. We don't need to understand what exactly that means, but usually it means that there's like very different behavior in the high temperature and low temperature regime. So I'm sort of lucky here that I can build on top of Evan and Anker's talk, because we know that, OK, so in the high temperature regime, it is very hot, so we represent using red color. And in the low temperature regime, it is the blue color. And we already know a lot of things about Gibbs states in the high temperature regime, where we know that they are fast mixing, and they're also classically easy to simulate. And there are reasons to make them physically less interesting. So now the question is, what about low temperature phase? Well, the first thing to say is that there are also many systems which do not have a phase transition. But maybe we better have one, because the concern is that if we do not, it might be classically easy all the way. Right? So now if we do have a phase transition, then the low temperature regime is really where the quantumness kicks in. And in particular, in condensed matter physics, we have this example of a really, really beautiful and remarkable system called the 4D toric code. It has two very magical properties. The first property is that it is a finite temperature topological order. If you don't understand what this means, just think of it as saying that the Gibbs state in the low temperature regime has polynomial quantum circuit complexity. In the meantime, it is also a self-correcting quantum memory, which means that if you start from an encoded state in the 4D toric code in the low temperature regime, the quantum information is stored for an exponentially long time. OK, so this is very great and very exciting. So can we use quantum computers to study low temperature physics now? Unfortunately, the barrier is that these systems are often slow mixing as well, which means that the quantum Gibbs sampler, in general, takes exponential time to prepare the Gibbs states. So this is really the fundamental challenge for us. And the question is, how should we address this challenge? So now we should think about how to overcome this slow mixing barrier. And a possible approach, of course, is to design more complicated Markov chains that will become fast mixing even.
Sorry, so on your previous slide,
yes.
So you mentioned this point, okay, self-correcting quantum memory that lasts for an exponentially long time.
Yeah.
Isn't this kind of going hand in hand with slow mixing somehow?
Exactly.
Okay.
Slow mixing has to be
both, right?
Yes.
Okay.
Slow mixing has to be like a prerequisite in order to have self-correcting quantum memory by definition.
Okay.
Great. So how do we overcome the slow mixing barrier? Of course, a possible approach is to design more complicated Markov chains that even become fast mixing at low temperature. But today, let's focus on simple Markov chains, just like classical and quantum Glauber dynamics, and see if there's something we can do here. So there is something that we could possibly do, because if we think about mixing time, it is a fundamentally worst-case notion. Mixing time says that any initial state converges to the Gibbs state after mixing time. So this leaves the possibility that this does not prevent fast convergence to the Gibbs state from a good and a simple initial state. So here we have to clarify these criteria. So a good initial state means that it converges to the Gibbs state quickly in polynomial time. And in the meantime, it also has to be simple, because otherwise it doesn't.
You just went the Gibbs state, but in the phase transition, we have more than one Gibbs state.
Well, I'm talking about the unique Gibbs state e to the minus beta h.
But below the phase transition, right?
Yeah.
You've got the magnetization up or down. I mean, there's a non-unique Gibbs state below after the
On
phase
infinite
transition.
graphs, right? On infinite.
Oh, what?
In the infinite case, you would have non-uniqueness, but I guess in the finite case,
Does each of the different phases with a different order parameter correspond to a different Gibbs state?
Yeah, actually, the unique Gibbs state e to the minus beta h is the equal mixture of the two things that you were mentioning. And each of them is called a metastable state. Right. OK, any other questions about this idea?
so would you expect like a typical initial state to mix quickly? Like, for spin glasses, there's a lot of recent works of showing that there are very isolated bad initial configurations.
Yeah.
That, is that the kind of thing? Or
Yeah, I will actually just discuss the simplest possible initial state, which is the, yeah. OK, so now it's sort of time to bring back our fundamental question about nature. Does nature have the ability to create topological order by itself in a finite temperature environment? And actually now we have the right picture for quantum Gibbs sampling, and we can ask this question in an equivalent and different way. And that would be, in the low temperature regime, can Glauber dynamics prepare the Gibbs state of the Fourier toric code in polynomial time from a simple initial state? And you can sort of see that this is a question that simultaneously addresses this physics question, but also it provides potential example for non-worst case mixing. So the goal of this talk is to convince you that the answer to this question is yes. And this is based on joint work with Tiago and Suwon Choi's group at MIT. And actually, our proposal is the simplest one possible. The claim is that if we start from the maximum mixed state and just put it in the finite temperature bath to let it run Glauber dynamics for polynomial time, then it should converge to the low temperature Gibbs state. And actually, there is a picture about what this is actually doing. So let's bring back our favorite picture. And our initial state is the maximum mixed state. And that state is actually the Gibbs state at infinite temperature for an arbitrary system. Right? If you think about e to the minus beta h at t equals infinity, which is beta equals 0, that is the maximum mixed state. And our idea is somehow that we take this state, which is at infinite temperature, and it's very hot. So you can see it's red. So we will take this initial state that is very hot, and we will suddenly throw it into the low temperature bath. And then we will just do nothing, and we will just wait. And somehow, we believe that if you just do nothing and wait, then after polynomial time, it becomes the low temperature Gibbs state, which is blue. And this dynamics has a name in physics called the quench dynamics. So depending on your perspective, you can either think of two things. You can think, well, this may be like a natural thing to try. Or you might be thinking that, how could this possibly work? How could you just cross the phase transition like this without paying a fundamental big price? So hopefully I will tell you that actually this is a good thing to do. So any questions? OK, so our conjecture is that there is polynomial mixing for quench dynamics. So for the 4D toric code on the 4D torus of side length L, where the system size is L to the power of 4, then the maximum mixed state starting from max mix state, we can run global dynamics for polynomial time at any fixed temperature strictly between 0 and the critical temperature to converge to the Gibbs state at temperature T. So why am I calling this conjecture 2? That's because there's like a very closely related classical problem, which is the 2D Ising model, which Anker just introduced, on a 2D torus of side length L with a system size L square. And actually, the classical analog of the max mix state is just a uniformly random initialization on the system of n bits. And if we initialize like that, we also have the conjecture that it should converge to the Gibbs state temperature T in polynomial time at any fixed temperature below the critical point. So this it sort of has been a major open question in the math literature. Any questions or comments about this? Yeah.
So do you expect polynomial degree to depend on how close temperature is to the TC?
Yeah, so the expectation is that the polynomial should be a fixed degree, and but there should be exponential dependence on the temperature before the polynomial.
Is conjecture to somewhat testable on numerical?
Oh, it's very testable. We will see.
Oh, okay. Nice.
Okay, so now you might be wondering, I already introduced this major open question in the math literature, and now I'm going to study the quantum problem, so which seems even more difficult. So how could we say anything about the quantum problem? Because on the top, we have like a classical Markov chain. And at the bottom, we have a quantum Markov chain that creates topological order. So it's even more complicated. So next, I will do two things. I will first tell you that actually, the quantum version is not fundamentally more difficult. There is some sense where we can actually reduce quantum to classical for this specific problem. And then I will convince you that both of these conjectures are true simultaneously. Okay, so it's perhaps a little bit surprising that we can, in some sense, try to reduce quantum to classical. But here's the idea. The idea is that because of the special choice of the initial state being the maximum mix state, this actually allows us to, in some sense, factor out the logical sector and focus on the syndrome sector. So I haven't defined what this means yet, but we will see it in a second. And then this viewpoint allows us to view the 2D Ising model and the 4D toric code as the same math model in different dimensions. So now they become much more closely related. Okay, so to tell you a bit more about how to reduce quantum to classical, let's introduce some very simple facts about quantum error correcting codes. So we will try to do a decomposition of the Hilbert space. If we think about any CSS stabilizer code, it is a commuting local Hamiltonian with x terms and z terms. And it has m terms, and we can think of their sign being labeled by a classical vector of length m, which we call syndrome vector. So for every eigenstate of the Hamiltonian, we can look at whether each x check or z check is violated or satisfied. And then we can assign a label of 0 and 1. And then finally, we get a binary vector of length m. So now we can group eigenstates into different syndrome subspaces. So this is just very similar and a bit more fine-grained than just energy eigenspaces. So this is syndrome subspaces, which looks like this. So we have the Hilbert space of dimension 2 to the n. It has 2 to the n eigenstates. And for different eigenstates, they have a different syndrome S. And different eigenstates might have the same S, and in that case, we put them into the same box. And the different syndrome will be in different box. So it turns out that the Hilbert space is a direct sum of all these different subspaces of equal dimension. This is like a sort of a standard fact about all error correcting codes. And furthermore, these subspaces are actually very simply related by just Pauli operators. So if you want to go from one subspace to another, you just apply a appropriate Pauli operator. Okay, So now this starts to look a bit more classical, right? And now we can think of what is the problem that we're trying to study here. So our initial state is the maximum mixed state, which happens to be uniform in every basis, right? So it is uniform in each subspace and uniform across subspaces. So the picture is like this. It is uniformly the same color in each box, and it's actually also the same weights across different boxes. Very easy. Okay, what is our final target? Our final target is the Gibbs state, which is by definition also uniform in each subspace, but it's sort of reweighted across different subspaces. And the probability or the weight of each subspace is proportional to the exponential e to the minus beta Hamming weight of S, which is precisely the energy of that subspace. And the picture looks like this, right? So you have different syndrome subspaces with different energy, and the weight is sort of reweighted according to the Gibbs distribution. Okay, so now the picture has become very clear. Because from the perspective of our dynamics, starting from the maximum mixed state and trying to converge to this Gibbs state, it's all about rebalancing the classical distribution across syndrome subspaces using random polyjumps. And this perspective allows us to just look at the syndrome and forget about what's inside the subspace. And that's fine because the different subspaces are always uniform anyways. So there's no reason to keep track of them. Okay, so now with this picture in mind, we can actually define the mass model that governs all of these dynamics. And that model is also very simple. Consider a d-dimensional cubical lattice with bits on squares and checks on edges, where the energy of the system is simply the number of violated edges, where each edge is sort of a parity check in the arithmetic code, checking the parity on the squares adjacent to that edge. And we will run Glauber dynamics on this sort of abstract mathematical model, which is also very simple. Just choose a random square. And then there are four edges on that square. And then we'll decide whether to flip those four edges or not. And the probability of flipping those four edges is given by the Glauber weight, where the delta E is the energy of it's the energy difference of if we were to do the flip versus not. So we either flip four edges or not. And there's a very beautiful coincidence that somehow this mathematical model is the universal behavior, where d equals 2 gives us the classical 2D easy model, and d equals 4 gives us the quantum 4D toric code. And if you look at this model, it has a consequence that the set of violated edges, which is just the syndrome patterns of a syndrome subspace, they actually have to form loops with trivial total homology moving around in a d-dimensional space. So later we will see what this trivial homology means. But for now, just think of this as like literally a very simple classical dynamics where loops are moving around in a d-dimensional space. Any questions? Great. So now it's time to show you the picture, right? So our perspective is that we have this Gibbs state that we're trying to prepare. But the content of the spin configuration or the quantum information is not important. We just factor them out and see the loop dynamics. So in the first picture, we have the Gibbs state of the 2D easy model at low temperature. You can see that there are zero colors and there are red colors and blue colors, where red means 0 and blue means 1. So this is a spin configuration. But you can forget about what's inside these colors and only look at their boundary, which are the small loops in the second picture, which is the Gibbs state of the induced loop dynamics in 2 dimensions. And then, because it's hard to see what's going on in 4 dimensions, we can visualize 3 dimensions. And this would be the X sector of the 3D toric code, which looks like a bunch of small loops in 3D. Okay. But then we can also look at the dynamics of how these things move. You can see that at high temperature, basically the Ising global dynamics is just a bunch of small clusters moving around. And occasionally they can become slightly bigger, but not too much bigger. And of course, exactly the same thing is going on here, where instead you forget about the spin, and you only look at small loops moving around in 2 dimensions. And these small loops can also move around in 3 dimensions like this. Okay, so this is the Gibbs state. It seems pretty simple, right?
This is the dynamics of the population dynamics of the Davis generator.
Yes. Okay. Wait. Okay. So now we actually have a new perspective to think about our conjecture. Our conjecture is that for the 2D Ising model and the 3D, 4D torical, and the 2D, 3D, 4D torus of Saturn's L, starting from the maximum mixed state in polynomial time at any fixed low temperature will give us the Gibbs state at temperature T. And then based on our previous argument, it actually suffices to show that if we start from the loop distribution induced from the maximum mixed state, then this should converge in polynomial time at any fixed low temperature to the Gibbs distribution of loops in 2D, 3D, 4D at temperature T. So somehow it's all about the same model in different dimensions. And understanding this model will allow us to say something interesting about classical and quantum models at the same time. Any questions?
So I'm trying to get some intuition for this. So somehow, in the classical case, okay, the distribute, like the Gibbs state has these very bad bottlenecks because it's hard to transition from mostly all plus to mostly all minus.
Yes.
Now the initialization you have there randomizes between the metastable states in the right way.
Yes.
And somehow around each metastable state, you don't encounter any of the sparse cuts. So somehow you would kind of expect that you locally mix in the right way, right?
Yes.
There are all these things like these Lovász-Simonovitz types of results about if you never encounter any bottlenecks in your Markov chain, then you mix as if you were an expander, even as long as you don't see the non-expanding cuts. Is that reasonable intuition for this, or?
I would say 2 things. So first of all, it's actually a very great intuition that, one way to think about how we are sort of managing to get around slow mixing is because our initialization has this very special structure that is already uniform in these different logical subspaces. And actually, one can argue that maybe the main reason for slow mixing in these systems, at least, is the bottleneck to go from one logical sector to the other logical sector, to mix between those, so to achieve uniform colors within the boxes. But because we already start from uniform colors within each box, we don't have that issue. And
so somehow, there are also these things classically in the last couple of years where the point is that if you have bad cuts, you're going to mix to some mixture over metastable states. You may not have the right mixing weights for the metastable states, but within the metastable states, you're correct.
Yeah.
And sort of here, you're fixed because you are starting with the right mixing weights on the metastable states.
Yes,
right?
Exactly. Yes. Mm-hmm. Yeah, that's a great remark. But I also want to say something different, something else, which is, life is not so simple. So we will see that some issues will arise, but in the end, they are not big issues. Yeah.
Because you kind of want to say that there's some kind of symmetry argument, and is there a way to kind of construct an effective chain that somehow already know the symmetry so that you can model all the different ones?
Yeah, I mean that effective chain is the loop chain, right? So that's what we're trying to do here. So if we forget about the content of each box completely, then the only thing that remains is the balance across different boxes, which is exactly what we are studying in this picture.
And once you model it out, this thing somehow should have no bottlenecks.
They don't have bottlenecks only because we are starting from the maximum mixed state.
But I thought once you model out, it should become like a fast mixing. Like I guess the question is like, is it itself a Markov chain, or is it's not exactly a Markov chain?
Oh, this is like this red dynamics is like a very well-defined Markov chain. But it's not obvious that once you factor out the logical space, it will become directly fast mixing. It will eventually work in our cases, but actually there are also more complicated cases where even if you do this decomposition, the remaining chain that jumps across different subspaces are still slow mixing.
So maybe I'll ask later.
Yeah. Okay, so now it's time to show you how this dynamics actually look like. So yeah, to summarize this page, so we promised earlier that in our specific dynamics, the 2D easy model and the 4D toric code are the same mass model in different dimensions. And this is how we showed this. Okay, so let's see how our initial state actually converges to a Gibbs state. And we will have like an x-axis and y-axis, where x-axis shows time, and y-axis is some well-defined and reasonable way to measure the closeness to the Gibbs state. So we will start from the bottom left corner and go to the top right corner. And the question is, what does it look like? It turns out that it looks like this with this very strange behavior, where if you look closely, so at the initial stage of the dynamics, somehow you very, very quickly make a lot of progress. You jump all the way from 0 to 0.4, and then you sort of have a turn and go on a different curve, which allows you to eventually converge to the Gibbs state in a sort of a different way. So it's apparent that this dynamics has a distinct two-stage behavior. And actually, we will see that this actually is the consequence of trying to jump across the phase transition. But it turns out not to be a big issue. So this is why eventually we have polynomial mixing time. Any comments about this?
So, sorry, what is shown in this? How? Like, can you explain a bit more this figure? What it means?
Yeah, this figure means that the x-axis is time, and the y-axis is how close we are to the Gibbs state in some well-defined notion. So what is going on here is that, okay, so this is sort of plotted in a scale of L to the power of 4. So this is the 4D toric code. But you can see that initially, the curve very quickly jumps from 0 to 0.4 in very little time compared to the full scale of L to the 4. And then somehow, the curve has like a turn, and then it goes to a different like behavior, and then eventually it will converge to the Gibbs state in time L to the 4. So we will explain what's going on here. And like I said, intuitively something has to go wrong, or something has to happen, because we are trying to jump across the phase transition. And it turns out to be not a big problem. Okay, it turns out that this phenomenon has been explored in the statistical physics literature, which is called zero-temperature quench. So here, I'm plotting two instances of the Ising model, where we are starting from a maximum mixed state, but we factor out the spin configuration, so we forget about the spins and only look at the loops. And we have two initial random samples of the initial state. They are just very random, chaotic big loops. And then we can try to run global dynamics at zero temperature, which would give us an indication of what's happening when you try to cool down the system. And this actually is the simplest example of using the Gibbs sampler to prepare the ground state in a greedy way, which is what Lin mentioned yesterday. So we can actually try to do this. And here is what will happen. You can see that very quickly the loop becomes significantly simplified, and now it sort of seems to be doing some kind of contraction. And there is a force that is driving the loop smaller and smaller, and eventually it will collapse. Okay, so this is absolutely amazing, right? So we can use the Gibbs sampler to prepare the ground state. If this is true in general, then we would have no problem cooling down our system and prepare ground states or low temperature Gibbs states. The problem is that life is not so simple, and we can see what's going on in a different random sample of the initial state, which looks like this. Wait, so what is going on here? It seems to be doing something very, very different. Initially, you also have this coarse graining of like a very big loop simplifying into some kind of shape. But now it turns into this metastable state, which is somehow two straight lines on this 2D system. Okay, so because we are plotting like a periodic boundary system on a torus, so a line physically means it's like a loop, non-contractible loop that wraps around the torus. And somehow we end up having two non-contractible loops in this system. And now, after we converge to this specific state, this state will just freeze here forever. It will never move because we are doing zero temperature dynamics. Okay, so wait.
Sorry, so it's zero temperature dynamics, but the randomness is like which site is being updated.
Yes.
Okay.
And this is turns out to be well studied in statistical physics, and physics call this enigmatic behavior in 2D. It turns out that with probably roughly 2/3, your zero temperature dynamics converge to the ground state, and with probability roughly 1/3, you freeze into a metastable state, and you will be forever frozen here. So now the question is, well, this seems to be like very bad news, right? Because how could it possibly possibly prepare the Gibbs state or the low temperature Gibbs state with this enigmatic behavior? Okay, so now here is the central thesis that I'm trying to convey. It turns out something similar also happens in higher dimensions for our quantum system. And our observation is that the zero temperature quench in higher dimension is even more enigmatic. But the point is that actually this turns out to be okay. We can, whatever enigmatic configurations that arise from this quench, we can deal with them in the second stage, which corresponds to this different curve that you saw earlier about converging to the Gibbs state. And the reason for that is because finite temperature global dynamics have the ability to eventually escape these enigmatic configurations. And let me explain a little bit more detail. So
the enigmatic configurations are only a property of the zero temperature. So if you're interested in the finite temperature, why do we need to deal with the zero temperature dynamics at all?
Yes, it turns out that it's a very good approximation of what's going on in the low temperature regime. So even if you start from literally here and run all the way low finite temperature dynamics, it will still have this ground state versus non-trivial loops, but the non-trivial loops will keep oscillating. And actually, that oscillation is what we're counting on here.
But so, I guess I'm a little confused. So the enigmatic states arise at the zero temperature.
Yes.
Now you set out the goal of like proving polynomial mixing for any t, less than critical that's bounded away from zero.
Yes.
So will your polynomial get worse as t gets closer to zero and the enigmatic states get harder to...
Yeah, I will explain. So it turns out that the expectation is that the polynomial dependence in system size will not change. What changes is the prefactor that depends exponentially on the temperature.
Okay, but something has to blow up and it's the prefactor.
Yes.
Because otherwise this is...
Yes, definitely, yes.
Okay,
yes. Okay, so more precisely, what's going on is that in the initial stage, the system quickly becomes either near the ground state, or it sort of forms topologically non-trivial configurations, each with constant probability. However, whatever arises from the initial stage, we can deal with them. Because in the second stage, we will see that these non-trivial loops that wraps around the torus, they actually perform a random walk with inverse polynomial bias. And Therefore, they will eventually meet with each other and annihilate in polynomial time. And this is the mechanism to have fast mixing. Okay, so now let me say a bit more about each of those claims. Yes?
And if you have only a single enigmatic loop, then it doesn't have anything else to meet. So
Great question. So I commented earlier that our math model has a very special property that is confined to the trivial homology sector. So you actually cannot
It
have
comes
a
from the spins.
yes. It's an
Otherwise,
image of
that's
yes.
where it transitions, so it has to be a second one.
Yes. So if you have a non-trivial loop, you have to have other loops that can annihilate with that. It's a very interesting property.
But then isn't like, so the annihilation is literally just that the two loops just kiss or something.
I will show you. Yes, they will kiss. Okay. Okay, so somehow in higher dimension, okay, so when physicists studied this, the toric code wasn't invented yet, so they couldn't foresee that there is like even more enigmatic behavior in 3D. So you can have like the zero temperature quench will sometimes give you the ground state with actually 50% chance. And we also give you two straight loops, which we have already seen in 2D. But it also gives you other enigmatic configurations like two skew loops. I won't even explain what is a skew loop. You can just sort of see that it's different. And then you have even more mysterious things like two straight loops and one skew loop, and so on. But all of that is OK. We know what's going on here. So what's going on here is that the initial stage of the dynamics is driven by a basic primitive called anisotropic curve shortening flow, which is just saying that large loops of length r contracts in time roughly r squared, which we clearly saw in the earlier Ising model. And it's also actually proven in certain special cases in 2D. And it's widely believed to hold in higher dimensions as well. And in the meantime, there is also a mysterious percolation phenomenon that creates multiple topologically non-trivial loops. However, we can rely on the following math fact, which is that edge configurations in our models all belong to the image of a boundary map, and thus they belong to the trivial homology. So different non-trivial loops have to be able to annihilate with each other. Okay. Yeah, so yeah, this implies that those topological non-trivial loops must be able to annihilate with each other. So now it only remains to understand how exactly does those non-trivial loops move. So our claim is that they behave like random walks. And the key question is, how does, so for example, let's forget about the even more enigmatic ones first and try to understand this key question. So how does a straight loop move at finite temperature in d dimensions? But now instead of saying words, I can directly show you how they move around. This is sort of the behavior of two straight loops at low finite temperature in 2 dimensions. You can sort of see that they slowly perform random walks and coming sort of close to each other. And eventually, they will meet at some point. And when they meet at some point, they will completely collapse like this. OK.
So is it purely diffusive behavior with no energy barriers?
Yes. Because OK, so what I've showed you is sort of a lucky example. There could be cases where you initially start from 2 straight loops, but they move in the opposite direction. That's equally likely. But because they are in diffusive random walks, they will eventually meet in polynomial time. So here is the claim. The claim is that these loops, they actually behave like particles doing random walk in d-1 dimensions. And they move with a non-trivial speed of theta 1 over L with like an exponential prefactor dependence on the temperature. It's actually not too hard to prove this if we make some suitable assumptions, such as that the loop is drawn from a distribution that is symmetrical in this d-1 dimensions. And once you believe this, you immediately can claim that this implies polynomial time to annihilate in d dimensions. Okay.
key here is this diffusive quantum particles, most complicated thing here, because you start from this right initial state.
Yeah.
Otherwise, it was patches, which is much harder.
Yeah. So basically, because of the special structure of our system, and the initial state, we know that the only thing that can happen when you run low temperature Glauber dynamics is non-trivial loops moving around. Nothing else that is more complicated can happen. And if we can understand that, then we can claim it's polynomial mixing. Okay, and actually this concludes my discussion about these specific models. So any other questions?
You have open boundary conditions in one direction, you have one loop material.
Right, so it turns out that for the 2D Ising model, in statistical physics, it's also observed that changing to open boundary condition doesn't change the behavior fundamentally, just small constants.
This one loop can also...
Yes, it can also happen with constant probability.
So I'm trying to visualize this in 3D. So in 3D, this reminds me very much like dislocation dynamics, but then these loops can only glide on particular planes. Is that the same thing here? Or?
Oh, I mean, in 3D, the loops will freely move in 2 dimensions.
Because so they each have a guiding plane.
Yeah.
And I think in dislocation dynamics, there were topological obstructions so that sometimes they cannot cross each other to annihilate like this.
Yeah, maybe we can discuss more offline, but I don't think there's any...
technology is still trivial, right?
Yeah.
Okay.
So I think because it comes from the edge boundary map that forces
Maybe
all those really exotic...
Yeah.
So now you prove those two conjectures, or?
No. I mean, proving them end-to-end will likely require fundamentally new techniques because it's non-worst case mixing, but you can prove certain small pieces, like how does loops move around if you make certain assumptions. So yeah, I should clarify that an end-to-end proof for a 2D Ising model is still like a very difficult math question.
So how do you mathematically characterize like in which direction the loop is moving? Maybe you have one part moving to the left, another part moving to the right.
Oh yeah, so if you're just having, because it's clear that if you have two loops that are separate, they are sort of independent particles, right? They don't really interact with each other. So they are doing independent random walks. And you can easily use the mixing time for a random walk to bound that the expected time that these two particles meet is sort of the same as your mixing time in the 1D line. Yeah.
So if you don't care about like true mixing, you just say I want to pick two points, and I just ask how fast does this converge to the expected, like the right value, and that still depends on the system size.
So what 2 points?
Like suppose I pick the right corner.
Yeah.
And then maybe so I just pick 2 points on, like they separate by 10 distant 10.
Yeah.
And then the system gets bigger and bigger. And then I run this dynamics. And then I just look at these 2 points. I just care about the value of these 2 points. And if you only care about these specific observables, then how fast does these two converge?
You are saying that if I don't care about converging to the Gibbs state, if I care about converging to the right distribution of local observables.
Yeah. Finite size.
Okay, I should say that the local you could imagine that your local observables is doing energy measurements. If that's the case, then it's also still important that you capture the right distribution in terms of energy, right? So that is sort of similar as saying that your loop distribution is converging to the Gibbs distribution. So depending on the observables you measure, yeah. Okay, great. So let me mention some intuitions that I learned from this that I hope could be more generally applicable. The first is that for quantum systems with phase transitions, if we naively run the greedy thermal gradient descent and an algorithm to prepare the ground states, it will probably get stuck, as we can see in this zero temperature quench. However, if the dynamics is finite temperature and it can explore the low energy landscape, it has a chance of getting unstuck. And this will probably take a while, but it hopefully can be polynomial time for some systems. And finally, maximum mixed state or like high temperature Gibbs states in general could be a good warm starting point for low temperature Gibbs sampling. And yeah, and I will mention briefly later how this could be used. Okay, so let me conclude by discussing a little bit about quantum advantage. So you know, this workshop is all about the same thing, right? So we want to prepare a simple initial state. And we engineer the system in a desired Hamiltonian. And we let the system evolve in a low finite temperature bus. So the question is, can this model efficiently simulate any classically hard computation? Or in other words, is there a quantum advantage in Gibbs sampling at finite temperature? So as Ankur said earlier, there is a complexity barrier to this question, because if your system is too general, it could be classically hard, but it could be also quantumly hard at the same time. So how do you find the line between classical hardness and quantum easiness is the key challenge. So in this paper 2 years ago, we constructed a family of commuting local Hamiltonians that is fast mixing, but at the same time sampling from the output distribution of measuring the Gibbs state at finite temperature is classically hard, assuming complexity assumptions. But this work really leaves some important open questions that we need to address. The first question is there complexity separation for estimating local observables, trace O times rho beta at finite temperature? Because in some sense, estimating local observables is what we believe to be the fundamental task of quantum simulation. And in the meantime, from a technical perspective, our previous techniques is really not applicable for this question. So it's a very important question in complexity theory. But then we also want to go even further and ask, is there a quantum advantage for physically interesting systems? So how do we really go forward and study these very, very difficult open questions? Well, let me bring up my picture one last time. So for quantum systems, we usually have this phase transition where we have low temperature and high temperature. At high temperature, it's fast mixing and classically easy and physically less interesting. And low temperature is slow mixing. And now the biggest challenge for our field is to understand where is quantum advantage? Well, presumably quantum advantage is in the blue region. That's why I put it there. But now maybe one way to go forward in understanding this question is to define this goal of trying to find classically hard systems with efficient Gibbs sampling in the low temperature phase. But again, how could we possibly have efficient Gibbs sampling in the low temperature phase when it's slow mixing? Well, as we discussed today, maybe sometimes the quench dynamics by starting from the maximum mixed state or some other suitable high temperature state could be a possible approach. And we should also try to develop other approaches as well, such as thinking about more complicated quantum Markov chains or thinking about metastable states. So that's all. Thank you.